This lecture goes into how we test the hypotheses when we're comparing two samples together. So when we do this, we select random samples from both populations to determine whether or not the population means are equal. So here we have some examples of some questions that we might test. Like, is there a difference in the mean value of residential real estate sold by male agents and female agents in South Florida? Is there an increase in the production rate after music is piped into the production area? So there are two major differences in the test statistic and the Z that we've looked at before. Basically, we're assuming whether or not we know the population standard deviation. And so when we're comparing two means, we're assuming that we don't know the standard deviation of the populations. And so in that case, we would use the t-test. And we have three requirements for this test. The sample populations are approximately normally distributed. They are independent of one another, and the standard deviations of the two populations are assumed to be equal. So when we do this, we can use the two-test means Z formula where we have x1 bar minus x2 bar. And we're looking at the two populations, assuming that they both follow the normal distribution, that allows for us to use the z-value. So remember that the test statistic follows the standard normal distribution when the population standard deviations are known. So note that since we're comparing the population means, if they follow the normal distribution pattern and are independent of each other, we are able to use the Z statistic for this analysis. The denominator of this portion, I wanted to kind of point out to you that that is going to be the value for the standard error for a difference in means. So let's look at an example. So let mean checkout time for the standard customer be mu sub s, and the mean checkout time for the fast lane be mu sub f. So remember that the level of significance is the probability of rejecting the null hypothesis when it's really true. We can use our z statistic here because we can assume that the populations are normally distributed and the standard deviations of both populations are known. The alternate hypothesis signs points to the right here. So this is a one-tailed, right-tailed test. So what we would do is we would go to the t-distribution, and in the table headings we would find the row labeled level of significance one-tailed test, and then select the column for an alpha of 0.01. And then we would go all the way down to infinite degrees of freedom because that gives me my z-value. And so the critical z-value from this table would be 2.326. And so that's what we're going to be comparing our calculated z-value to. So we assume that the population standard deviations are 0.40 and 0.30 as shown in the table. Then we take the sample and calculate the test statistic to get a z-value of 3.123. Our decision rule was to reject if our z-value was greater than 2.326. So my calculated z-value is greater than my critical z-value. So therefore, we make the conclusion to reject the null hypothesis and make the interpretation that the fast lane method is faster. So how do I compare two means using t? So we have the test statistic that we use to compare two means is our t-distribution, assuming that the population standard deviations are not known. So we have three requirements: that they're approximately normally distributed, all of our populations are independent of one another, and the standard deviations of those two populations are equal. So in most cases, like I said before, we don't know the population standard deviation, so we're going to substitute our sample standard deviation S for sigma. The pooled standard deviations and pooled variance should only be used after careful consideration when background research indicates that the population standard deviations are nearly equal, when the sample size is large, and the conditions may be adequately checked with data. The benefits of pooling the standard deviation greatly diminish as your population increases. So when we look in the next slide, we're going to look at an example to use another method to compare sample means to determine if the sampled populations could reasonably have the same mean. So here we're looking at Owens Lawn Care manufactures and assembles lawnmowers and that are shipped to dealers throughout the U.S. And they have procedures that have been proposed for mounting the engine onto the frames. And so they want to know, is there a difference in the method's mean time to mount the engines on the frames for the lawn owners? So here we have the results of a sample of 5 employees' time using the Wells method, and we have 6 that are timed using the Atkins method. And so the first thing we do is we state the null hypothesis, where population mean of the Wells is equal to the population mean of the Atkins. And then my alternate hypothesis is that they're not equal. We set our level of significance here because we're maybe doing an exploratory method. We're going to use an alpha of 0.1. And so based on 5 observations and an alpha value of 0.1, we can now determine what our t statistic is. So remember, now we've got our degrees of freedom being 9 because I have 5 employees on both sides. So I'm sorry, we have 5 employees on the Wells method and we have 6 employees on the Atkins method. So 5 plus 6 is 11. But with degrees of freedom, we subtract our number of separate samples. So 5 plus 6 minus 2 gives me 9 for my critical value. And so when I look up degrees of freedom of 9 on a two-tailed test with a 0.1 significance level, my critical values are going to be plus and minus 1.833. And so then I take those values and I plug them in to calculate my sample standard deviations. Then, using that, we're going to pool the sample variances, which are basically the sample standard deviations squared, so that we can then calculate our t-value. And so, of course, Excel and other software can kind of spit that value out for you, which is quite nice. But these would be the formulas that you would use if you had to calculate this by hand. In our previous examples, we've assumed that they had the same variance, even though we didn't know what the population standard deviations were. We just assumed that they were equal. So in many cases, that is a reasonable assumption. But what if it's not? If it's not reasonable to assume that the population standard deviations are equal, then we're going to use S sub 1 for the first population and S sub 2 for the standard deviation of the second sampled population, instead of using their population standard deviations. And then we have the values N1 to represent the number of observations from the first population, and N2 to represent the number of observations from the second population. And so then we're going to adjust the degrees of freedom downward once again, because our number of samples is going to decrease, right? So we have our number of observations from group 1, number of observations of group 2, and then subtract our number of groups to get our total degrees of freedom. And so this gives us a larger value of the test statistic that we use when we determine whether or not we're going to reject our null hypothesis. So after observing there's more variation in the store brand, it does not seem reasonable to assume that the population standard deviations are equal. So looking at this, we're going to decide to use the t-distribution and assume that the population standard deviations are not the same. And so when that happens, we end up using um, our unequal population standard deviations calculation. And so we have 10 degrees of freedom with a two-tailed test at the zero point 0.10 significance level gives me a critical t-value of negative 1.812 and positive 1.812. And so then we use the formula shown here on the screen to find our test statistic. And we end up calculating a t-value of negative 2.474. And our negative 2.474 is going to fall in the rejection area. So our decision is going to be to reject the null hypothesis and conclude that the mean absorption rate for the two towels is not the same. So what happens if I have dependent samples? So what does this mean? So this is going to be situations where our observations are paired with each other. So when the dependent samples are in use, we assume that the population distribution of the paired differences has an average or a mean of 0. And so here in a couple slides, we'll go over an example of that. So here we're looking at appraisals, and so we're comparing two appraisal firms. So if the two appraisal firms are reporting similar estimates, and sometimes Shaded Egg appraisals will be the higher value, and sometimes Bauer Real Estate will be the higher value. So one thing we've got to keep in mind, though, is that the mean of the distribution of the differences will be 0. On the other hand, if one of the firms consistently reports larger appraisal values, then the mean of the distribution of the differences is not going to be 0. So once again, if the mean of the differences is 0, that's going to be my null hypothesis. We would conclude that there is no difference between the two firms' appraised values. And so here I'm looking at equal, not equal. So this is a two-tailed test. Because we're just looking at whether or not there's a difference. We don't have any directionality to this. So since it's a two-tailed test and we're doing this at the 0.05 significance level, we need to do 0.025. We have 9 degrees of freedom because we have 10 homes. And so the critical values are going to be plus or minus 2.626. So now what we need to do is we need to compute the mean, which is 4.6, and the standard deviation, which is going to be 4.402 of the sample differences. Then we're going to compute the test statistic t, and we find that our calculated t-value is 3.305. So we decide to reject the null hypothesis because our test statistic, our calculated t-value, is going to be greater than our critical t-value of 2.262. So the two firms' appraised property values are going to be different. So in other words, this means that each firm is appraising the same property with a different value. So we're looking at dependent and independent value, samples. The first type of dependent sample is sometimes referred to as the before and after study, or the paired samples that we just looked at. So if we look at an example of nickel SNL, for example, what if we had assumed that we had two independent samples rather than dependent samples of real estate? So if that were the case, we would have pulled our variances of our samples in order to calculate t, and that would give me a value of 0.716, which is much less than my critical value of 2.101. So in that case, the null hypothesis would not be rejected. Whereas the hypothesis test on dependent samples eliminated the variation between the values of the properties and focused only on the comparisons of the two appraisals for each property. So here when we're doing power calculations, this goes back to that discussion of our type 1, type 2 error. So remember that type 1 error is rejecting your null hypothesis when you should not have. Type 2 is failing to reject your null hypothesis. Power of a test is the probability of correctly rejecting your null hypothesis, and the probability of doing so is 1 minus beta. And remember, in hypothesis testing, we want to keep alpha and beta low, but there's that inherent trade-off that as you make alpha go down, beta is going to go up. So when we look at our type 2 error rate, this is where we're looking at if the alternative hypothesis is actually true. So what would be the chance that we make a type 2 error, meaning we fail to reject the null hypothesis even when we should have? The answer for this really isn't quite obvious. If the true population average is very close to the null hypothesis value, it's going to be very difficult to detect a difference and end up rejecting that null hypothesis. If the true population average is very different from the null hypothesis value, it's much easier to look at that difference. So this is really going to come down to your beta value. So your type 2 error rate is really going to depend on the effect size that you have for your analysis. So what are some things that we can do to increase power and decrease our type 2 error rate? We can get a larger sample size. We can figure out ways to decrease our standard deviation, which is basically, it has the same effect as increasing our sample size. So if we have a smaller sample standard deviation, we have a better chance of distinguishing the null value from the observed point. If we increase our alpha, so that's going to be if I go from a 95% confidence interval to a 90% confidence interval. So our alpha value is going to be that area outside of my confidence interval. It makes it much more likely that we will reject our null hypothesis. And something we might want to consider is using a larger effect size. So if the true mean of the population's in the alternative hypothesis but close to your null value, sometimes it's going to be harder to detect that difference.